Okay.
All right. Welcome everybody to this iteration of GOCC. We're very happy to have Brittney talking about an arithmetic measure of width for convex bodies. Before we start, I'd like to mention our community guidelines. We are all learning, everyone has something to contribute, and no one has all the answers. With that being said, Brittney, take it away.
All righty. Good morning, folks. Or I guess good afternoon for most of you, but for me, good morning. I'm going to talk to you today about an arithmetic measure of width for convex bodies. This sort of project took inspiration from a lot of different places and a lot of different fields. So we're going to have a little bit of Ehrhart theory. We're going to have a little bit of discrete optimization. There's a little bit of sprinkle of commutative algebra. There's some number theory that's hidden in the background. And so it was a whole lot of fun to work on. Um, this is joint work with my advisor, Jesus de Loera, and my also sort of advisor, Chris. Um, and Jesus is sort of lives firmly in the land of discrete optimization. He does a lot of different sorts of things, but I would say most recently, most things take that flavor. And Chris sort of lives in this land of commutative algebra. And again, many, many, many other things, but for now, for the story today, that's what we're going to talk about. All right. And you can ask yourselves, okay, what does discrete optimization and commutative algebra have in common, right? They sort of feel like very distinct different fields. But laying in this middle chunk are two objects that I like a lot called polytopes and semigroups. And those are going to be sort of the main characters of today's story. And so when you put these two perspectives together, then you get me sort of laying in this nice little intersection here. All right. So first you might ask yourself, okay, let's talk about discrete optimization. It's sort of a stranger place to take inspiration for, I think, than many of us used to thinking about. And we take inspiration from a field called from an idea called lattice width. All right. Lattice width appears in many important areas in mathematics, specifically in something that we study called integer optimization, but it even appears in sphere packing problems and, strangely enough, in computer graphics. Okay. Now, for some of us, we haven't thought about notions of width, maybe since our first year's analysis class. So I'm just going to sort of go through what basic Euclidean width is, what lattice width, and then I'm going to build up to that new idea of arithmetic width. All right. So I'm going to start by fixing K to be a convex body. And I'm going to say the Euclidean width, this quantity here, is calculated as follows. Okay. So first, I'm going to talk about saying the width in a fixed direction. And by direction, it's going to be the normal vector for a hyperplane. Okay. And we're going to say the Euclidean width is the distance between two hyperplanes that sandwich your convex body in that direction. Okay, so this quantity here would be our Euclidean width of this convex body in this direction. Okay. Now, in contrast, okay, this works better when I can click through slides, so you guys are gonna have to deal with a lot of scrolling today. um, but in contrast, the idea of lattice width is very, very similar, except there are two sort of key differences here. The first being our normal vectors have to be lattice vectors or rational vectors, right? That'll work too. But also, the direction vector here now matters, not just in direction, but in magnitude as well. So if I want to compute the lattice width, all right, okay, let's go back to, I guess we'll talk about that in a second. We'll go back to Euclidean width real quick. Um, Here, right, if we want to talk about the Euclidean width not just in a direction now, but of the entire convex body, what we want to do is we want to take the smallest of the widths over our non-zero vectors, okay? And it's not too hard to see that when you have a polytope, you're going to get one that's parallel to a facet here. And so this is going to be our Euclidean width here, this 5 over root 2. And you can figure that out with whatever high school or vector calc you want to use, high school geometry, all right? But as I was sort of hinting at, lattice width is very, very similar, okay? The width, the Euclidean width was obtained in this direction here, which had a normal vector of 1, 1, right? And so that's already an integer vector, and yet the quantity differs here because the magnitude of that vector is different. So what you get is it's going to be the Euclidean width in that direction times the magnitude of the normal vector. So you're going to get a distance here of 5 as your lattice width, all right? And this sort of is designed to encapsulate this idea of narrowness or thinness of polytopes, all right? It's great importance in integer optimization as we ask ourselves things like feasibility problems. And that has to do a lot with, okay, are there going to be lattice points in certain areas of certain shapes? All right. Now, if you are kind of thinking geometrically about this, which I think a lot of us do, right? I say the lattice with this here is 5, and I can take 6 copies, parallel copies of that hyperplane, and cover all of the lattice points of this shape. And that's not a mistake. In particular, you're going to have a nice little inequality that basically says you can always do this. Okay? But sort of stranger things can happen here. All right. Now I want to think about the lattice points in this convex body, and I'm going to take this as my normal vector, which means I'm just going to pluck off the x coordinates. So here I pluck off 0. There's nothing to pluck off to get 1. There's no lattice points here. This point maps to 2, 3, and these 2 points will map to 4. But there's nothing here, right? There are these gaps. And lattice width, while it does a good job in encapsulating this idea of narrowness, it doesn't really account for these gaps where we're narrow enough to squeeze between the lattice in any kind of real way. And so what we did is we cooked up an invariant called arithmetic width that's designed to sort of think through these gaps a little more carefully. Okay, and so that's what I'm going to talk to you about today. This is a new sort of construction. There is a similar construction from the torque variety people, but it's not quite the same. All right. So in order to define the arithmetic width, I need to define the first main character, the arithmetic range. And it's going to be sort of what we've described. I want you to think about taking all of the lattice points in a convex body, hitting it with your favorite integer linear functional, and looking at the set that arises. I'm going to call that the arithmetic range with respect to the direction that you picked. Okay? And the size of that set is going to make up something called the arithmetic width. Now, in this example that we just did, right, we had 0, 2, 3, and 4 appearing as our range when we take this as our direction vector. And I'll reiterate one more time that when we talk about in a fixed direction, right, we're just taking the size of the arithmetic range in that direction. But when we just say arithmetic width, we mean the minimum, the smallest that this set can be for non-zero integer vectors. Okay. Now, we had 4 things appear in our arithmetic range, but that's not going to be the minimum here, right? I can go ahead and cover the lattice points with these 3 lines, all right? And when you cover the lattice points in the hyperplane, any lattice points on the same hyperplane will get mapped to the same place into the linear functional. So that kind of tells you the size of the arithmetic range here. But it's also not going to be unique, right? I can also choose just this and cover it this way. Okay. So that makes up the arithmetic range and the arithmetic width. Now, the arithmetic width behaves in a ways that you would want it to behave. The first kind of, I'd say, common sense thing we would want to happen here is that if I translate my convex body by an integer vector, The arithmetic width and the arithmetic range, in some sense, shouldn't really change. Okay. Secondly, unlike with lattice width, if I take two parallel vectors, my arithmetic width will actually end up being the same. It's invariant under the magnitude of the direction vector. And if you think about this from an integer programming perspective, that's kind of a really nice perspective, because finding short vectors in lattices is a historically difficult problem. And this C here talks about the phenomenon of just covering it in hyperplanes, okay? So basically this is saying that the lattice points can be covered in some number of hyperplanes when you fix a direction, and the arithmetic width is the same as that number of hyperplanes. Okay. And the last one says that we're pretty much good to just study the minimal problem. We don't really need to study the maximal problem because that's a theory that's well understood. Ehrhart theory. All right. You can always find direction vectors where you can pluck off all of the lattice points in your convex body to go to different places under that linear functional. And you kind of do it as it's described in this picture here with a sort of skew. All right. So here, right, this lattice point, they all go someplace different. Okay. And so those are the sort of like, I would say, common sense things we would want for this thing to be well defined and nice enough to work with. All right. Now, these gaps that we're talking about are really going to be the main character, and they're going to help us understand structural properties for the arithmetic range, and thus help us say something later about the arithmetic width as we dilate convex bodies. All right. And if you're familiar with lattice width, you might for a second think, okay, these are very, very similar objects, and they are, but we have a couple of key differences, right? And the one I want to highlight is mostly just here, right? Lattice width does not pick up on this gap behavior, but our arithmetic width is going to pick up on this gap behavior, okay? And later on, we're going to talk about this idea here, okay? Which is we're going to get some sort of quasi-periodic behavior under dilation. Okay. With that, we're almost prepared to talk about some main results. All right. And so people in discrete optimization care about these gaps and lattices, right, for these feasibility problems. But there are other fields of math with other perspectives that also study these gap objects. Okay. And so now I'm going to talk to you a little bit about how these gaps appear in the field of factorization theory. Okay. So this is the theorem for sets of length from factorization theory. It's a behemoth of a theorem. I don't ask that you read this giant paragraph, all right? It's got a lot of words with a lot of different ideas in it. And I think, like most things in combinatorics, it's going to be better explained with an example rather than trying to get you to read all of the details. So let's go ahead and do an example. Some of you guys are probably familiar with numerical semigroups, but forgive me for repeating. I'm going to just go through a couple of key things that we need here. So we say S generated by G1 through GD, a subset of the non-negative integers, is a numerical semigroup if the three conditions hold. First, 0 is in your semigroup. Second, we want to be closed with respect to addition. So if I add two things in the semigroup, I need to stay in the semigroup. And lastly, the complement in the non-negative integers needs to be finite. We call this a cofinite condition. Okay. So if you've never seen this before, I want you to think about the numerical semigroup generated by 4, 5, and 6. Well, I can take no copies of these generators to get 0. Can take one copy of 4 to get 4, and so on. I could take two copies of 4 to get 8. I could take 4 plus 5 to get 9, and so on. right? We want to be all of these integer combinations, non-negative integer combinations of 4, 5, and 6. But because we have a finite complement, we can also specify a numerical semigroup in terms of its gaps in the non-negative integers. So the only integers that are not in this semigroup, non-negative integers, are going to be 1, 2, 3, right? Because we don't have them, and then 7. So it's an equivalent way of talking about a semigroup, is just in terms of its gaps. Okay. Now, in factorization theory, one of the big things they care about is this idea of factoring things non-uniquely, right? When you think about prime numbers in the most traditional sense, you've got your fundamental theorem of arithmetic, things factor uniquely. But in this additive context, things factor highly non-uniquely. So as an example, if I take 12 in this semigroup, I can write it as 3 copies of 4 or 2 copies of 6. And so this is what we mean by non-uniqueness. And to each of these different factorizations, we can associate a tuple, all right? So this, I read this as I take 3 copies of the first generator plus 0 copies of the next generator plus 0 copies of the next generator, and so on. And so these 2 factorizations give me these 2 lattice points. And to each of these lattice points, we can associate a length just being its coordinate sum. So here we get just 3 and 2. And we stick them in a set, and we call that the length set. And this is the set that giant theorem from before is about, at least in this nice enough setting. All right. So here's what this theorem says. And to do that, I need to pass to a slightly uglier semigroup. So we're going to consider the semigroup generated by 22, 79, 91, and 190. And we're going to think about factorizations of the element 4,180. All right. And so you spit that into your favorite computer and ask it for your sets of length, because I don't know about you, I don't want to factor this out by hand. And we get this as the set of lengths. So as a reminder, these are the coordinate sums of all of those tuples we get when we look at the additive expressions to represent this in terms of these generators. And if you look carefully at this, you'll notice, first of all, suggestively, we've written it in 3 distinct parts here. Next, you might notice, okay, well, this piece in the middle here is an arithmetic progression, right? I just go plus 3, and so on. And really, that's what the giant paragraph is saying. It says the set of lengths for elements in numerical semigroups, when you take sufficiently large elements, forms an almost arithmetic progression of some fixed step size. And the step size is associated to the numerical semigroup, not the element. So if you take different elements, you're going to get the same step size. Okay. And we call things, objects like this, an almost arithmetic progression. And the way that I like to think about an almost arithmetic progression, it's like you take an honest to goodness arithmetic progression, and maybe near the extremes, you just sort of push out a couple of terms. Okay? So here, right, I'm missing 181, 184, and so on. But this part here is that honest to goodness arithmetic progression. All right? So that's really what this paragraph here is saying. We also can talk about these in terms of its gaps, right? If you know where it starts and you know where it ends and you know what your step size is and you know what your gaps, you can recover this as well. All right. And that's something we're going to use in a second. Okay. So for our first main theorem, this idea of almost arithmetic progressions is going to come into play. All right. Now, if you are thinking back to the perspective from the discrete optimization people, they're going to go, okay, so that's nice, but where's my polytope, right? Like that's really what the bread and butter is here. So we need to find our polytope. Well, we had a bunch of lattice points associated to things, to factorizations. And so we're going to do what most people do and look at the polytope containing those lattice points. So there's an object called the numerical semigroup polytope. So you form it as follows. You take the convex hull of 1 over the first basis vector, 1 over the second generator times the second basis vector, my bad, all the way 1 over your last generator times your last basis vector. And the nice thing about this object is it is going to encode those factorizations. So it turns out that the lattice points in the nth dilate of the numerical semigroup polytope corresponds to the different factorizations of that element in the semigroup. And that's really nice because now we can take a statement that's in this algebraic setting, look at it geometrically, and see what other conclusions we can reach. So we can actually view the same giant paragraph structure theorem for sets of length as follows, which is saying if you take a sufficiently large element in the semigroup and you fix your direction vector to be the all ones vector, we have that the arithmetic range of the nth dilate of the numerical semigroup polytope in that direction is just an almost arithmetic progression. Okay. So now we have a big structure theorem about one specific type of polytope. And that's a little bit suspicious, right? Why would it only hold in this setting, right? And so our sort of first response was, okay, well, we could probably do better than that, right? From the perspective of the semigroup people, they only care about that polytope, right? They're not going to care about others. But from the perspective of maybe our discrete optimization people, we're going to care about other convex sets. And so we asked ourselves, okay, how far does this structure go? And so we arrive at our first sort of main theorem. And I'm going to call this the structure theorem for the arithmetic width of a convex body. Okay? And there's a lot of words here, but let me sort of just walk you through intuitively what is happening here. What this basically is saying is that when you fix your favorite integer linear functional, the arithmetic width range that you get in that direction is going to form an almost arithmetic progression. But it's not just any arithmetic progression. There's a couple of nice things happening, right? The first off is that there are constants, t and t prime and lambda, that only depend on your convex body. So even as we dilate, we're not going to get different constants, okay? Those constants are associated to just the convex set, not which dilation you are looking at, okay? The next kind of fixed thing is that as I'm dilating, this region here, there we go, this region here is going to be responsible for this almost the arithmetic progression part, and these regions here are going to be responsible for the almost part, okay? So these are where my gaps are happening, and I can think about t and t prime as some sort of fixed distance here. So as I am dilating, this region is getting bigger, and this distance here is fixed. So it's just getting wider and wider, but the same fixed distances kind of dragging along in translation. All right. And these regions are where we have the gaps. So the gap structure is sort of just going to get translated along as we dilate. Okay. And while the proof is a little bit technical and annoying to read, I'm going to sort of give you the big picture, and it comes down to the same idea. But essentially what you want to do is dilate your convex body so that you're large enough that you can stick a ball in it that definitely has to have a lattice point, okay? Now, once you dilate past that region, you can think about dragging the copy of that ball this way and another copy of the ball this way, right? That fixed distance idea. Okay. And as you drag them out further and further apart, this region in between grows. And because of convexity, you're going to have lattice points in between. And so here, you're going to pick up your arithmetic progression. And again, in this fixed distance, as we drag it out, you can have your gap behavior. Okay. And so that's the first sort of main theorem I'm going to talk about today. Okay. Now, looking back to the theorem for sets of length, a really nice corollary that we're going to get is that any finite set of integers is going to appear as the arithmetic range of some rational simplex. Okay? And so that is kind of nice. We don't have any constructive way at the moment to like find which one it is, which dilate of which numerical semigroup polytope, but any finite set of integers can be thought of in this way, and that's kind of nice. Okay. Now, if you've been around these two long enough, right, you'll think, okay, I'm dilating something, might as well be a polytope. And if I'm dilating polytopes, I might as well find the Ehrhart theory in it all, right? It has to be there lurking in the corner. And this story is no different. If you've not heard of Ehrhart theory before, I'm just going to give you the world's quickest TLDR on it. But Ehrhart theory cares about counting lattice points in dilates of rational polytopes. Okay? And in particular, the counting function forms a rational quasi-polynomial in your dilation factor, where the degree and the period depend on the geometry of the rational polytope. All right? And if you've never seen a quasi-polynomial before, here's sort of our first canonical example in the rational case. So if I take this guy to be my polytope, and I count the lattice points in each dilation, and we express it in this polynomial way, if my dilation factor is even, the number of lattice points is expressed like this. If it's odd, the number of lattice points follows this formula. Okay, and so that's this idea of a quasi and quasi-polynomial. When you restrict to a period, you can think about it just being a polynomial, but you're going to have that nice periodic behavior. Okay. And with that, I can talk to you about our Ehrhart type results in this setting. And so what we want to do is we want to look at the arithmetic width as we dilate a rational polytope. Okay. Now, what we get are the following two results. The first says that if I fix an integer linear functional, the arithmetic width is eventually quasi-linear in the dilation factor with period dividing the denominator of the polytope. All right? Which, if you've ever thought about Ehrhart theory before, that doesn't feel so surprising, right? You're taking all of your lattice points, you're dilating it. Ehrhart theory says we should get some sort of quasi-polynomial there, but I'm hitting it now with an integer linear functional, so linear, quasi-linear, that feels about right. But what I find really remarkable is the second part, which says that even when I descend to the minimum, right, it is still eventually quasi-linear in the dilation factor. So what does that look like in practice? Well, let's just zoom in on this example real quick. This here is which dilation of this polytope, and this is going to be my arithmetic width. All right? Now, if we look at the coordinates of this polytope, I've got a 1/3, a 1/2, and a 1/6. If I dilate this polytope by 6, that is going to be the first time we are a lattice polytope instead of just a rational polytope. And we call that the denominator of the polytope. And if you count the color-coded dots, which I've colored for each period, right, there are 6 of them. All right, and so this is that sort of quasi-linear behavior we're getting for the arithmetic width for this guy here. Very similar idea over here, right? I've got a 1/2, a 1/2, and a 1/5. So I've got a denominator of 10, and I actually get a periodic function where this is 1 period. And I know it looks like it could have a smaller period. I promise you, if you look at the data, it does not in this case. Okay. But again, each of these distinct colors refers to a distinct class, mod 10. Okay. And so that's what's happening with the Ehrhart type results in this setting. And in order to prove something like this, we're going to have to think a little bit more of that idea that as we dilate our polytope, we are translating the gaps kind of uniformly in some sense. So the proof sort of has the 2 following main ingredients. The first is sort of what we just said, which is that if I now add a copy of the denominator of the polytope to my dilation factor, the number of gaps I get is the same. Okay? And once again, this is just that idea that as I dilate, I am translating the gaps. All right. The next is that if I take 2 dilation factors that are congruent mod the denominator of my polytope, then the directions that attain the arithmetic width are going to be the same. Okay, and this is kind of nice because as you dilate your polytope, different mod classes can actually have different vectors that obtain the arithmetic width. But when you are congruent mod the denominator of the polytope, the way that I like to think about it is that the lattice points sort of near the pointy bits feel the same, and they're sort of relative to the boundary in the same sort of way. Okay? And again, this is the same idea. As I dilate this polytope, all right, well, I have a gap here, and I am translating that gap uniformly throughout the lattice. And additionally, as I'm not picking up any new gaps once I do this. Okay. Now, we've talked about gaps from the idea of polytopes, and we've talked about gaps from the ideas of commutative algebra, but there are gaps in discrete optimization as well that go beyond just lattice width. And one of those is called the integrality gap. All right. If you've never thought about linear programs before, that's okay. What I want you to think about, most important, I think, for us today, is that when we say the feasible region of a linear program is going to be a polyhedra. And if you take a bounded one, you're going to get a polytope. Okay, so where you can find solutions for today lies in some sort of polytope. All right. Now, what can happen when you are trying to maximize in a fixed direction for just your arbitrary polytope? Well, I can get that the maximum is rational. All right. But a lot of different optimization problems are better described with integer linear programs because, for example, you can't take half of a person, right? So we sort of want the next best thing. And to do that, your feasible region is now just the lattice points in that polytope, okay? So in this case, here would be my maximum. And we'll notice there's sort of a gap between these 2 solutions. And that idea is studied in the integrality gap. And there are a lot of different types of integrality gaps that you're going to find in literature. Typically, we study it in terms of some sort of constant multiple. But different folks study it in terms of additively, where they vary some fixed parameter in your linear program. Today, we're going to define what I'm going to call the additive maximum and minimum integrality gaps are. And what you do is you take the maximum that your linear function attains on your polytope, the real one, right? Okay, so this guy, minus the maximum you attain on its lattice points, and I'm going to call it the maximum integrality gap. And we also have the minimum integrality gap, right? You take the minimum on the actual real polytope minus the minimum on the lattice. Or, well, I've swapped them, but you get what I'm saying, all right? And it turns out this idea of thinking about dilation as translating gaps lets us say something kind of nice about these two quantities. Okay, so if you've thought about these before, it might not be too surprising. But if you take two dilation factors that are congruent the modulo of your denominator of your rational polytope, you get that these quantities are the same. Okay, so you get that your maximum integrality gap and your minimum integrality gaps are just the same. Okay, so this tells us that as we dilate, we're actually going to be growing quasi-polynomial as well. Okay. And now for our last sort of main result, my advisor has very specific perspectives, and what he basically said was, okay, well, no one's going to care about this if you can't compute it efficiently, right? No one's going to care about the arithmetic width. We might have just traded one problem for another. And there's some hope there, right? There are polynomial time algorithms to compute the lattice width, but not so much here. And so that's what we're going to talk about today. So sort of the first main ingredient, if you've thought about these ideas before, is you ask, okay, well, what does Barkanoff's algorithm tell us here? And so if you've not heard about this before, you can encode the lattice points in your polytope as a Laurent series. So how do you do that? Well, you take the lattice points as exponent vectors for monomials and add them up, all right? And that gives you your Laurent series. And Barkanoff's algorithm basically says that in polynomial time, I can take this potentially infinite series, all right, and express it as a signed sum of rational expressions for some generating functions, okay? And they do this with some sort of nice cone decomposition, if you're familiar with those sorts of things. But the key sort of thing here is you can do this in polynomial time, right? It's not so impressive if you think about it in terms of a polytope, but it's a little more impressive when you think about polyhedra, right? You've got infinitely many lattice points. We're taking an infinite expression and giving it some nice finite compact expression in polynomial time. And these sorts of things really form the basis of a lot of different software, like if you've ever heard of Latte and things like this. Okay? And so we wanted to look at what this does in our setting. Well, there's a nice little part 2 of this theorem, which, again, it's a paragraph, but what I'm going to basically say is that there is a polynomial time algorithm to give us a very similar expression to the one attained in Barkanoff's algorithm for a projection of the lattice points in a polytope. And really, when you're taking your arithmetic range, that's really what you're doing, right? You're just taking a fixed projection with codimension 1. Okay? And so this is going to let us, at least in fixed dimension, have a polynomial time expression to compute the arithmetic width in a fixed direction. Okay? And that's sort of what it's being said in this first part here. All right? So if you take the input bit size of your polytope and the direction vector, and you fix a dimension, all right, you're going to get an algorithm that computes the arithmetic width in a fixed direction in polynomial time. But we sort of run into some natural obstacles when we think about computing it just the arithmetic width, right? Now we no longer have a fixed direction and we want the minimum. And this is a little more difficult, okay? It turns out we're only going to get a singly exponential time algorithm because while we can sort of trim down the different directions to test to some sort of nice polynomial time, not polynomial time, we can trim down to some sort of finite, you're going to get a lot of them. In particular, they're going to correspond to the lattice points in this metric difference of a blah, 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 right? And as you dilate, right, you can pick up more and more and more lattice points, right? So even though I have some sort of fixed input bit size, right, I've got 5 hyperplanes here. As I dilate, I'm going to get more and more lattice points, but I can sort of still have the same fixed input size for my polytope. And so we're really only getting this nice singly exponential behavior, which, while not the most amazing fun thing, still means I can run my code in some decent time, so I'm somewhat happy. Um, and so that sort of is the lingering question for this project that we have, is that is there some sort of nice polynomial time way to do this? Um, Lattice width, again, there's some nice methods using some approximation algorithms, but we haven't found anything in this setting. All right. Thank you for having me. Oh, that's cute. I haven't seen that. I've been off Zoom for a bit. Any
Uh,
questions?
any questions for Brittney?
So can I ask a very naive, slightly unrelated question?
Yes, please.
So like what are the benefits of like doing discrete optimization over like something that's continuous? I guess you give the example of like, oh, people, you can't have half of a person.
Yeah. I mean, so that's sort of the thing, is like many, many actual real life situations have to be modeled with this integer linear program. They don't, they're not better modeled by the real version, because the actual solutions you obtain are not ones we'd want. So for example, like you could have ones where you have no lattice points on the boundary, right? But maybe you have some solutions really, really close. Okay. And in a maybe more high-tech version, there's something called semi-definite programming, where you can take semi-algebraic sets or cones and other things to optimize over. And so I can take like an ice cream cone, right? So you take the cone over your circle, your unit circle, and you're going to get points arbitrarily close to the boundary. Okay. And so there's really a fuzzy behavior of the lattice points. It's not enough to just like think about the ones on the boundary.
I see.
Yeah.
Yeah, that makes sense. Okay. Yeah, thank you for your talk.
I suppose another answer to that is that integer programming is much more hard than linear programming. So maybe linear is for something to optimize. That's easy. That's also there exist algorithms in polynomial time, but integer programming is it solves problems with a different difficulty. So it brings something more. Yeah, thank you for your amazing talk. I really liked how you try to give intuition behind the whole proof. And on that, I want to ask, okay, that's amazing how you put the sphere inside and then you pushed it away and it has this constant width. And how would an argument look like why in the middle it's arithmetic? Because you said in
Yeah.
the middle between the two spheres, it's
Yeah. So let me go. Actually, let's not do that. Let's do this. Let's go back to that picture. Okay. I mean, essentially, your convex body lives in some sublattice of the integer lattice, right? Some coset. And that coset has a fixed step size when you hit it with your linear functional. And that's that same sort of progression that you're going to be getting. But essentially, right, this slice is big enough to have a lattice point. This slice is big enough to have a lattice point, which means if I go like this, the circles sort of in those pre-images of the lattice will be big enough to have a lattice point. So everywhere I can have a lattice point, I'm going to have one in the pre-image. And I'm going to get that step size by thinking about the ambient coset of the integer lattice that this guy lives in.
Okay, but doesn't the amount of lattice point also play a role, or?
So this guy, as I'm dilating, just gets bigger and bigger and bigger, right? And so it's stretching
Yeah.
out the arithmetic progression part, so that chunk in the middle,
Mhm.
right? But the gaps here are the ones that stay fixed. So as you dilate, you get more lattice points here.
Okay.
Maybe
Okay.
I'm not understanding the question.
Most probably I'm not understanding exactly uh, the translation between what exactly is the arithmetic progression in this polytope.
Yeah, let's do this, right? It's kind of like when you have the set expressed this way, as you dilate, you're just picking up more terms of a sequence here, right? But this part grows and this part just sort of translates, but structurally stays the same. And so this is that part in the middle.
Okay, so these integers are just the indices, so to say, of the cuts. They're not counting number of points or something like that.
Yeah. Yeah, because a bunch of
Ah,
different lattice points go to the same place if they are on the same like copy of
yeah,
that
yeah, okay.
plane. Yeah.
Okay, thank you.
All righty. Thank you for having me.